Good afternoon, everyone. In this talk, I will introduce our research on the vulnerabilities in Master Lock smart locks. This is joint work with Danielle, Lira, Tsai, Miro, and Nadia Heninger. Smart locks are a kind of digital locking mechanism. They are quite popular. The global market size was estimated at $2.8 billion in 2024. Smart locks are security critical since they are integrated into doors as a trusted component for access control, and they are closely related to physical security. There are many use cases for smart locks, including front doors, offices, hotel rooms, Airbnb rentals, etc. So, are smart locks really secure enough to guard people's property and safety? Previous studies looked at August, Danielle, and other smart lock vendors. These studies found many vulnerabilities, including transmitting passwords in plain text, lacking replay protection, and allowing attackers to bypass revocation by setting phones offline. Compared to many other vendors, Master Lock fared well. Rose and Ramsey analyzed 16 smart locks. Master Lock was one of the 4 locks for which they found no vulnerabilities. When Knight, Lord, and Riff discovered that the Bluetooth communication between the Master Lock product and the phone was encrypted, they chose not to analyze it further. Compared to previous studies, our work focuses more on the reverse engineering of the communication protocols and encryption algorithms in the Master Lock D1000 smart lock and its companion Android app, Master Lock Vault Enterprise. We found 5 attacks, including exceeding access, which allows unlocking after access is revoked; session replay, which enables attackers to replay recorded Bluetooth low energy, abbreviated BLE, sessions to redo operations such as unlocking; audit log tampering, which allows anyone to forge audit events on the audit log server and potentially hide suspicious events. There are 2 other attacks, clock tampering and malformed messages, which we will not cover in this talk. You can refer to our paper if you are interested. Before we go to the main topics, let me introduce essential background information. To implement access control for smart locks, one obvious option is to connect locks to Wi-Fi so that they can directly communicate with servers. But to reduce power consumption and support offline usage, Master Lock chooses to use the device gateway architecture. As shown in the diagram, the smart lock does not connect to Wi-Fi. Instead, it communicates with servers via the user's phone. To dig deeper into security, we analyze both the BLE communication between the phone and the lock, and the HTTPS communication between the phone and the servers. Next, I will explain the previously mentioned BLE. BLE is designed for short-range communication, consuming significantly less power while maintaining a similar communication range compared to traditional Bluetooth. Master Lock smart lock becomes active only when the user interacts with it by tapping the touchpad. Then the lock will start to send advertisement packets so that the user's phone can discover it. BLE transmissions follow the generic attribute profile, abbreviated GATT. In the advertisement packets, the lock announces all available services by UIDs and manufacturer-specific data containing device ID to distinguish each lock. For each service, there are characteristics also identified by UIDs. For the phone and the lock to communicate with each other, the phone as a BLE client will send write requests to specific characteristics on the lock as a BLE server, and read from characteristics to receive responses. We reverse engineer the app to find the expected service and characteristic UIDs, and also the whole BLE communication process, which are necessary to implement a custom client for our attacks. Before going to the actual attacks, we want to mention the challenges we faced during reverse engineering of the app and our solutions. Master Lock has employed various obfuscation techniques to try to protect their Android app from reverse engineering. We will focus on 3 of them: encoded and encrypted constants, calling native functions, and loading DX dynamically. This code snippet is an example of obfuscated code in the Master Lock app to give you a flavor of how it looks. The first technique is storing constants encoded and encrypted, and they are decoded and decrypted at runtime. In this snippet, we can see a part of the obfuscated code to decode a static RSA private key embedded in the app. Line 7 shows the reconstruction of the RSA private key from modulus and private exponent, and the previous lines are the decoding of corresponding constants. Our solution is to use dynamic partial evaluation. That means we emulate the inputs and arguments of the current method and code execution so that we can get the decoded values without caring about how the decoding actually works. We only need a JVM instead of an Android operating system, and we do not need to run the whole app. However, there are still issues that prevent simple partial evaluation, which will be introduced next. The next obfuscation technique is calling Android platform native functions. We are looking at the same snippet, but on the part of decoding the constants, and more specifically, the arguments passed to the static method $$a. We can see that the code is calling native functions in system clock, view configuration, etc., followed by fix-up calculations such as bit shifting. These calls create challenges for partial evaluation because standard JVMs do not include Android platform packages or native libraries. While it is possible to replace these calls with constants, we instead make these native functions return placeholder values because it requires less work overall. Using any reasonable placeholder values will work, since the code has to be deterministic across devices and environments. As a result, the constants after fix-up calculations are guaranteed to be the same or have equivalent effects. The final obfuscation technique is storing critical code in separate DX files encrypted as APK assets and loading DX dynamically. This snippet shows a part of the code to read the DX file from inside a zip archive decrypted from an APK asset. JVMs cannot handle it automatically, since the DX loading packages are missing, and JVMs cannot read Delvit bytecode in DX. Our solution is to write a custom DX loader, modify from the official one, and convert DX to Java libraries, which can then be loaded into JVMs. Now we move to the main part, protocols and attacks. The authentication flow works as follows. First, the app authenticates to the server using the user's organization, email, and password. After successful authentication, the app can request a pair of session key and profile corresponding to the log from the server. Then the app transmits the profile to the log, which encodes the session key and user ID, and is encrypted by a symmetric key embedded in the log. The log can decrypt the profile and obtain the session key, so that the log and the phone share the same session key without transmitting the key in plaintext over BLE. After the session is established, the app can send encrypted commands to operate on the log, such as unlocking. There is also a revocation mechanism for user access. Before requesting session keys and profiles, the app fetches a list of logs to which the user has access. When the app scans for BLE devices in the vicinity, if the log is not in the list, the app will not show the log as found, even if it is discovered in the scans. If the administrator revokes the user's access, the log is removed from the list sent by the server. the server will not generate session keys and profiles for a lock if the user no longer has access to it. However, what about previous profiles generated before revocation? Actually, the lock still accepts them, leading to the exceeding access attack. As you can see, there is an expiration date corresponding to each profile returned by the server. Attackers can save session keys and profiles and use them with custom clients implementing the BLE protocols between the phone and the lock. Alternatively, attackers can use the official app with the phone offline to prevent updates of the list of locks from the server. The lock can only verify profile validity by the expiration dates encoded in the profiles. What makes this vulnerability worse is that profiles are valid for 9 months. This negatively impacts a variety of settings, such as offices, hotels, Airbnb, etc. Now let's focus on the encrypted BLE sessions. After exchanging the session key, all BLE communication inside the session is encrypted using AES CCM with an incrementing nonce. It means that the lock chooses a starting nonce n for the first ciphertext C1 sent to the phone. To encrypt the next command, the phone uses the nonce n+1. The lock uses the same nonce to decrypt, then encrypts with nonce n+2, and so on. Since the nonce is incrementing monotonically, replaying a previous ciphertext within a session means that the lock will use a different nonce when trying to decrypt, which will fail. However, there is a pitfall. We found that the lock picks the same starting nonce for each session. If 2 sessions transmit the same messages in the same order, the ciphertexts are exactly the same. Attackers can record a whole BLE session and replay all ciphertexts until the one corresponding to a target operation, such as unlocking. After inspecting the phone lock communication, we shift gears to target the phone server communication. We discovered that the app uses static secrets embedded in the app to authenticate to the audit log server without any user authentication, although the static secrets are stored obfuscated. In addition, the log entries are neither encrypted or authenticated, leading to the audit log tampering attack. We reverse engineered the static secrets embedded in the app and the binary formats of log entries. Here are 2 kinds of log entries, wireless unlock and unknown. Since log entries have associated indices, and the app will send all new events since the last upload. If attackers want to hide their activities when there are other users having access to the log, they have to upload fake events to take the spot of real ones. For example, they can replace their wireless unlock events with unknown events. Since unknown events are not displayed to users, attackers can hide their unlocking activities. After explaining the attacks, we move on to our disclosure process and mitigation for them. We disclosed all 5 attacks to Master Lock, and they held a video meeting discussing every vulnerability with us. We appreciate their serious attitudes towards our disclosure and their prompt and detailed response. Master Lock chooses the validity period design to balance functionality and security, because the lock cannot contact the server directly for a revocation list. Setting a longer validity period supports offline unlocking. For example, if the lock is for a cabin in the forest, there is likely no cellular network or Wi-Fi for the phone to connect to the servers. However, for D1000, the validity period of profiles is 9 months, which is too long in our opinion. The harm of delay in effective revocation overtakes the benefit of convenience, and regular users are not aware that profile validity period is so long. Master Lock told us that the 9-month validity period is due to a previous firmware bug that caused the clock on the lock to jump forward in time. Since not all users have installed the updated firmware with the patch, Master Lock set the profile validity period much longer to avoid locking users out. Master Lock decided to push firmware updates more aggressively and shorten the validity period to 1 week. For the session replay attack, Master Lock confirmed that it was a firmware bug specific to D1000 that the lock picked a fixed starting nonce. Shortly after we disclosed the attacks, Master Lock said they have a fix in the next firmware update, and D1000 will choose a random starting nonce like other products. For the audit lock tampering attack, our suggestion to Master Lock is to add message authentication codes to log entries using the already existing symmetric key shared between the lock and the servers. After some discussions, Master Lock told us that they have fully mitigated this attack, although we do not receive further technical details from them. Finally, I want to share what we learned from these vulnerabilities. Encryption alone does not ensure security. Both protocol design and implementation are hard. Secure products require in-depth analysis and testing. Once again, we find that encrypting embedded secrets makes analysis harder, but it's not enough to secure authentication. It is still an open problem to establish secure channels between IoT devices and remote servers without trusted intermediaries. There is a standard called Matter on the secure integration of IoT devices over different protocols, but it requires trusted components to provision devices and issue certificates. Master Lock needs secure channels across IP and BLE, but the user's phone cannot always be trusted. That's all for my talk. You are welcome to look at our paper for more details and the other attacks. Thank you.